Okay, today we're going to be talking about arc length. All right, now in arc length, let's say we had a function, right, defined on the xy plane, right, by f of x, and I want to find the length from some value a to some value b, right? So what I mean by arc length is the actual length of the curve here, right, which we'll call L. All right, so just kind of from here to here, the length across there. All right, now one thing we can do is, all right, we'll take the approach that we did when we defined the integral and we're trying to find the area under the curve, but in this case, we're finding a different quantity. All right, so we'll start with an approximation. All right, now here this curve has some kind of interesting shape, right? So it's not very easy to find the length. Right, but what is easy to find the length of is of a straight line. So the goal here is, well, what if I partition the interval across, have this one be my initial, right, x0, x1, etc., where b is my xn, right, however long my partition is. And I want to zero in, or just focus in, I should say here, on one of these intervals, right? Just a general interval, right? So just to keep it as general as possible, let's say I call the interval, from x sub I minus 1 to x sub I, right? And again, I'm just choosing one in between a and b, right? These values, x sub I minus 1 and x sub I, are in the interval, and let's say in this particular interval, the function has this behavior. All right, keeping very general, not necessarily that it is this function itself, but this is a portion of the curve, right? L represents the whole curve there. All right, now it's going to be a regular partition. What that means is that the delta x, the change along the x, is always going to be consistent. The delta y will fluctuate just depending on the behavior of the function. Right? But for here, I'm going to evaluate, or I'm going to approximate the length of the curve, right? Because the length of the curve is this length here. But what I'll do is I'll actually have my approximation to be here, and I'll call this L sub I. All right? And now we have a straight line, right? And actually this becomes rather easy to calculate, right? Because if we look at, okay, here, I could call this delta x, right? The change in x. And this delta y sub I, right? Because again, delta x is fixed across the interval. We have a regular partition where the values of delta x are all the same. Delta y sub I will fluctuate depending on the behavior of the function. Well, what we have here is a right triangle where L sub I is the hypotenuse, right? And the values of delta x would be here x sub I minus minus x sub I minus 1. And then the value of delta y sub I would be y sub I minus y sub I plus 1. Okay. All right. Now to calculate the L sub I is just applying the Pythagorean formula. So we have, So we have my L sub I to be equal to square root of delta x squared plus delta y sub I squared. Okay, now we're going to do a little factoring here. I'm going to factor out this quantity here, right? Even though it's not in common here, that's okay, I can do that, right? If I factor out delta x squared, but I'm taking the square root of it, I can write it outside of the root as just delta x. And what I'm left inside is 1, and then the quantity here, delta y sub I over delta x the whole quantity squared. Okay. All right. And now this quantity here, change in y sub I over change in x, is, if we think of it, it's a slope, right? It's the rate of change of the y over the rate of change of the x. Right, and when we started in our first semester of calculus, we had a theorem called the mean value theorem, right, where we had the essentially what it said, if we had the rate of change between 2 points, the average rate of change here, right, then there exists a point inside of the interval. We'll call it x sub I star, and it's an element of, that's what this symbol means, of the interval x sub I minus 1, x sub I. All right, so there's a value of this x sub I star in that interval where the derivative evaluated at this x sub I star is equal to the rate of change, the average rate of change along the interval. Okay, so now we can do a little substitution, and now I have an approximation here for my L sub I. That would be the quantity root 1 plus the derivative of this x sub I star times delta x. All right. Now, looking up here, this L sub I is just one of these in here, right? L sub I. All right. Now, how do I find the actual value of L itself? Well, I can just set up a sum, in this case, a Riemann sum. Right? So what I can do is to find L, right, and sorry, this is approximate here. What I can find to find L is I can set up the limit as n goes to infinity, right? Because right now, if you notice here, right, y goes to infinity, my approximation here, right, there's error here, right? But how do I make a better approximation? I include more intervals in the fixed interval AB, right? So I just make delta x smaller and smaller and smaller, right, till it becomes infinitely small. And what we've seen before, this limit converges, right? As long as f satisfies certain conditions. In this case, our condition is that f is continuous. Right, so here, we'll set up a Riemann sum from I equals 1 to n. Here, 1 plus f prime of x sub I star. This whole quantity squared delta x. All right, so we have this quantity where delta x is approaching 0 as n goes to infinity. All right, and this x sub I star is also approaching the values that are kind of trapped in this interval as they get smaller and smaller and smaller. Okay, all right, and we've seen that this is a Riemann sum that converges, and the convergence of a Riemann sum is a definite integral. So this value this Riemann sum converges to the integral from a to b of the square root of 1 plus f prime of x squared dx. All right. Okay, and that is our formula. Right? So once we're asked to find the arc length and we're given some interval, then we just recall, well, I need to find a derivative, I need to plug it in, and then it just comes down to evaluate an integral. Right now, there's an alternate definition of this formula if you have a function that is just defined as along the y, right? So instead of f of x, let's say here we wanted to use the values c and d, And instead of y equals to f of x, our function was defined as x equals to g of y, right? G of, excuse me here, g of y. All right, in that case, we'll have an alternate definition here. The L would be the integral from c to d of the square root of 1 plus g prime of y squared dy. All right. Same formula, just the functions are defined with a different variable in mind. Okay, so now let's take a look at how applying this formula. All right. At this stage in our calculus journey, we are limited to the types of integrals that we can evaluate. We have our basic integrals where we just use the power rule, and then some substitution, some integrals, right? But it's very narrow, right? So the types of integrals that we can solve for the arc length, they're limited, but that's okay, right? In a later chapter, we will introduce a wide array of techniques that will allow us to even find arc lengths of much more, of a wide variety of functions. But for now, let's do a problem that we can easily approach here. Okay, so here, let's try an example here. So for this example, I'm going to find the arc length. The arc length of y equals to x to the 3/2 between x equals 1 and x equals to 4. Okay. All right. So given a problem like this, right, basic problem here, so let's just consult the formula. All right, so we're going to need an integral. All right, so it's an integral defined along dx, excuse me here, all right, and then the derivative of the function, all right, and I'll square it. So let's start off with that. So my f of x is the function x equals to, f of x equals to x to the 3/2. All right. So if I take the derivative, f prime of x, 3/2 x to the 1/2. Okay, so now let's find the arc length. So L, they give me the values of x, so that's going to correspond to the upper and the lower bounds. Okay. All right, and then we'll have the root of 1 plus then the derivative, the whole thing gets squared dx. All right, now let's work through this here. So rewriting this with squaring the function there, so we get 1 to 4 square root of 1 plus 9/4 x dx. Okay. All right. So now the question becomes, can I integrate this? All right. Now it's a square root function, or it's a composition of a square root function. So it looks like I am going to be able to, right? And mainly what tells me that I can with the techniques that I know now, it's essentially just substitution, is that this value of x is linear, right? It's not squared, right? It's going to make this a more straightforward approach using a u substitution. All right, so we'll do the appropriate substitution. All right, so again, I'm going to use u to be the quantity 1 plus 9/4 x. Okay. All right. And that means that du will be 9/4 dx, or just setting it up for my substitution, we'll have 4/9 du equals to dx. Okay. All right, so far, here's what we have. This whole quantity is my u, so we get root u, or u to the 1/2. And then my dx will get replaced by 4/9 du. I'll just throw the 4/9 outside the integral since it is a constant. All right, now the only thing missing are the limits of integration. All right, now we do not use 1 and 4, right? Those correspond to my x variable. I am no longer an x. All right, I am in my u variable. So in order to do that, I need to take the lower bound and plug it into my u function, right? So u of 1 will be 1 plus 9/4, which is equal to 13/4. All right, so that's going to be my lower bound. My upper bound, I plug in 4. All right, so when I plug in 4 into my u function, I get 1 plus 9, which is 10. So that would be my upper bound. So now I have my limits of integration in terms of u. Okay? All right. And now we have a straightforward integral, right? We just apply the power rule. So here we get 4/9 u, 1/2 plus 1 gives me 3/2. Divide by 3/2 or multiply by the reciprocal is the equivalent operation, evaluated at 10 and 13/4. Okay, so now let's keep moving along here. We get 8/27 for our constant. For our values here, we get 10 to the 3/2 minus 13/4 to the 3/2. So here we could leave it like this. Sometimes you can rewrite this if you're so inclined to. When you have something to the 3/2, it's equivalent to saying 10√10. Right? Because if you cube it, right, one of the squares you can take the root of, and then you'll have another factor left over. The same thing here. So we have 13√13, right? But the 4 is actually a perfect square. So if I take the square root of 4, that's 2. Raise it to the 3rd power is 8. Right. So there we go. That's just a little simplification. I would accept either of those answers there, right? As long as, they're both it's going to be irrational. So that's about as far as I want to take it, right? If you actually wanted some kind of linear or some kind of approximation, we can just plug that into our calculator, whatever that is. Okay, what we want to get from here is mainly just, we have the formula. How can I apply that formula? All right, our integrals right now would be very basic, right? Once we get to chapter of techniques of integration, we'll be able to use this formula for a wide variety of functions.